All right, physicists, welcome to our second lecture video of Physics 105. In this video, we're going to talk about electrical forces and electrical currents. We already talked about electrical forces a little bit in our first video, but now we're going to add what if you have more than one force, and then we're going to add the idea of current, which is when charges move around. Okay, so just to revisit quickly what we did last time, we had electrical charge in units of coulombs. Remember that in this story, coulombs is to charge like kilograms is to mass. So it's an amount of charge. Now, the reason that charge is different from mass is that while mass is always positive, particles can have either a positive or a negative charge. So for instance, here's your hydrogen atom. It has the electron hanging out on the outside of the proton. But if you look at the total charge of that object, of the hydrogen atom as a whole, it has a zero charge because the minus E minus 1.602 times 10 to the minus 19th coulombs, that quantized charge on the electron, is balanced by the plus E charge of the proton. The neutron, of course, doesn't have an electric charge. Now, most objects are like this. Most objects like you have an overall electrical charge of zero, despite the fact that we're made of large numbers of charges, and a complicated system like your body also has quite a bit of current running around in it in terms of your nerves and your heart beating and all of that sort of thing. So we need to think a little bit harder about that. How do you get one charge being acted on by the electrical forces of many other charges? So that's one of the main ideas that we're going to talk about today. So the other thing that we talked about last time that's extremely important for us to remember is Coulomb's law. Coulomb's law describes the electrical forces on objects with electrical charges Q1 and Q2 separated by some distance r. How does it relate? Well, the Q's go on the top, Q1 times Q2. Those are like the masses in Newton's law of universal gravitation. The r's are how far their centers are from one another. And this number in front is a big number, right around 9 times 10 to the 9 newtons times meters over coulombs squared. Remember, the meters squared are to cancel out the units of the distance, and the coulombs squared are to cancel out the units on the charges. Now, remember also, Coulomb's law is different from Newton's law of universal gravitation, because while gravity in that simple form is always pulling things together, in this form already, if you have two positive charges, they're going to repel each other apart. If you have two negative charges, they would repel each other apart. On the other hand, if you have a positive and a negative, they pull each other together. Okay, now, today, to get ourselves to the point where we can add up electrical forces, we're going to be summing vectors once again. Okay? Now, this is going to be very similar to the way that we added vectors together last semester. Now, remember, a vector is just a pointer, and if you add two pointers together, it can be kind of tricky because we add them tip to tail. So here, for instance, if I had my A and B vector, here's an A vector and a B vector. Now those could be displacement vectors, they could be electric field vectors, they could be electric force vectors, they could be gravitational force vectors, whatever. The reason why it's tricky is because you slide this over and add the vector from the tip of one to the tail of the next. And then this is the sum vector, A plus B. Now that's the geometry of adding two vectors together. How is it that you actually do that algebraically? Well, a good way to do it is to split up your A into an x and y part. So there's your AX and your AY in this picture. You split up your B into an X and Y part. So there's your BX and BY. And notice AY is positive in this picture, BY is negative, so they are going to partially cancel each other out. One is, if these were forces, one would be pulling up, one would be pulling down. So the overall pull in this S sum vector of A plus B is entirely horizontal because the AY and the BY are pointed in different directions. On the other hand, the AX and the BX are both pulling in the positive X direction, so they add together. Okay, and in principle, you could do that in 3 dimensions. Now, one thing that is easy in 2-dimensional problems, if you're not thinking too hard about it, remember, you know, if you have a triangle, here's your A, B, and C. In this case, your sine of the angle is going to be the opposite over the hypotenuse, so that would be the B over C in that picture. The cosine of that angle would be A over C in that picture. So if I draw a vector in my xy plane and I label the angles like this, so here's my vector, could be anywhere, and I want to, and I put my angle in like this, and I label my angle 0 is on the plus x axis, 90 is on the plus y axis, so this is the same as saying 0 in radians, pi over 2 in radians, pi 3 pi over 2. You can use either degrees or radians, but be careful on your calculator, of course. If I want to split this vector up into here's my vector A. If I wanted to split that up into an AX and an AY, the way that I would do it is I would have AX is A, the length of that arrow, times the cosine of the angle. Okay, so that gives me this length. And then the way that I would get my AY is by A times the sine of that angle. Okay, and you can also go back from the AX and AY to get what the direction is. And of course, since tangent of any angle, if you have a triangle like this, B over A would give you the tangent, opposite over adjacent to that angle, B over A. This is a right triangle. You can go ahead and find the angle. Of course, you have to be a little bit thoughtful. You can't just use your calculator output directly if you have labels from 0 to 360. You can just use your calculator output if you're in this first quadrant, but not otherwise. Okay, so let's just do a quick example. It says in unit vector notation, what is the sum A plus B if A is 4 plus 3? So the I is in the x direction, j is in the y direction. So this would be 4 over 3 up. So that's your vector A is going to be somewhere over here. So there's your vector A. And your B is going to be minus 13 in the x direction, so way over here, and then plus 7. So something that's not quite to scale, but not too bad. You can hear the lawnmower in the background here. Okay, so if I add this vector and this vector, got a good lawnmower, I know I'm going to get something that's going to be up there. A plus B. All right. Now, because I haven't drawn it quite to scale, it's not quite right. But just to make sure we know how to do that algebraically, if I have my A vector is 4, 3, This is my x, my y part, meters. And then I represent my b is going to be minus 13 in the x direction, plus 7 in the y direction, also in meters. To add those two vectors together, I need to add the components. So I'm going to take 4 plus minus 13. Okay, so that will give me a minus 9. And then 3 plus 7 will give me 10. Okay, so if I had drawn this correctly to scale, this would be pointing almost at a 45-degree angle from the minus x-axis over here. Okay, now that's my vector. So I could also write that as there's my a plus b equals, or I could also write this as a plus b equals minus 9I plus 10j. And I would want to have a 9 meters times I, 10 meters times j. Okay, now it asks me what is the magnitude and direction. Well, to find the magnitude, here's my minus 9 plus 10. There's my vector. If I want to find the magnitude, that's how long this vector is, I would just use my Pythagorean theorem. Okay, so the magnitude, and the way we write that is with the absolute value types of lines on the sides, is going to be the square root of 9 squared plus 10 squared. Okay, and you can stick that in your calculator, and that should give you around 13.45 meters. Now, it also asks you for the direction of a plus b. Remember, this is 0 degrees, this is 90 degrees, this is 180 degrees. There's not one right way to do it, but the way I would do it is to look for this angle first, and so and then I would take 180 minus that angle to find this angle. So that angle, that phi would be 10 over 9. Here's my 10, 9 triangle. That would give me my tangent. Well, let me put it this way. Tangent of that is going to give me be 10 over 9. So a tan, or inverse tangent on your calculator, you might have 10 over 9 is equal to 48 degrees. Okay, so then your direction on this is going to be 180 minus 48 degrees, which is equal to 132 degrees. All right, so there's your direction, there is your magnitude, and there is your vector. Okay, so that should hopefully be review from Physics 104. Now, why is that going to be useful to us in this class? Well, it's going to be useful because we're going to be summing electrical forces. And in systems with more than 2 charged particles, the net force on each particle is the vector sum of individual forces. Now, that's not different from Physics 1. That's the same. When we added forces together, we did a vector sum of all those forces. So if I have a force in this direction and a force in that direction, on the same particle, I have to add those together as vectors. And in this picture, what I'm trying to get across is that you could, in principle, have this particle acted on by lots and lots and lots of other particles. And in the usual systems, okay, in usual uncharged systems, your body, for instance, is made of gobs and gobs of charges. So the fact that you are stuck together to yourself, that is because of electrical forces. Okay, ultimately that is electrical forces, but you don't need to necessarily think about it in those terms. So let's try to think about this just a second. So this is a problem. I've given you one similar to this on your homework this week. It says you have a particle of charge minus q is right here. It's right in the middle. Is surrounded by two circular rings of charged particles. What are the magnitude and direction of the net electrostatic force on the central particle due to the other particles? Hint, consider symmetry. Okay, now I want you to look at this. Let's just consider, to start out, this particle, that particle, and how they are pulling on this minus q particle in the middle. Okay, so if I have a plus 4q and a plus 4q, and this is a minus charge, whoops, minus q, plus 4q, let me see if I, no. Okay, now, consider that since these have opposite charges, I'm looking for the forces on this one in the middle. Okay? Now, the amount of force that this guy over here, this plus 4q and the plus 4q on the bottom, they are both going to be pulling on that central object in the middle. And since they have opposite charges, opposite signs of charges, this is a positive charge, this is a negative charge, they will be attracted. So this charge in the middle will be attracted upwards towards the one at the top, and it will be pulled downwards by the charge at the bottom. However, if you look at the form of Coulomb's law, since my q times 4q and q times 4q, the stuff on the top is the same, and the stuff at the bottom is the same because these are the same distance from the central charge. These two vectors are perfectly matched, and they cancel out. So the up pull is canceled by the down pull, and these two particles, the net force that they apply on Q is 0. Now, if you look at this, there's a lot of these types of situations in this particular picture. So, for instance, this minus 2Q, this would be repulsing the central charge, this minus 2Q. This would also be repulsing, but they have balanced forces. So they do not contribute to a net force. Same way with these two. Okay, so I'm just crossing out the pairs of particles that lead to balance. So this plus Q, balance. Minus 7Q, balanced. And so now if I look at the only charge here that's not balanced, that would be that plus 2Q at the top. Okay, so what direction is it going to be pulling? Well, I have a positive charge there and a negative charge there. Opposites attract, so it's going to be pulled upwards in that direction, in the plus y direction. And so the force net for all of those particles is just going to be 1 over 4 pi epsilon naught. Remember, that's just a number. 2Q, that's this charge, times Q. So that's going to give me a Q squared, and we're taking the absolute values because we put in the direction by hand in this case, over this little r squared. And I would put this in the j hat direction. That's my y direction. Okay, so we're done with that problem. So you really can simplify some of these problems if you consider symmetry. Here's another type of problem. It says the figure below shows 4 arrangements of charged particles. Rank the arrangements according to the magnitude of the net electrostatic force on the particle with charge Q, start greatest first. Okay, so I want you to notice the types of particles that are doing the pulling. The Q over here is the same every time. The electron and the proton each have a charge of the E, that elementary charge, but they have an opposite sign. So that means that they will be pulling or pushing on Q in opposite directions. Okay, so what I want you to consider here is two things. Is it pushing or is it pulling on Q? For each of these forces. And because this bottom particle is closer to Q, capital Q, it's going to have a larger force. If you're closer, you have a larger force, and if you're farther away, you have a smaller force. So that's going to determine the size of the vector. So let's just try to think about this for a second. All right. So what are the two vectors here? Well, this is a Q and a Q, so it's going to repel this, so it's going to be pushing away. Okay, I'm drawing a exaggerated big arrow because it's pushing out. And this one is also going to be pushing away. It's going to be pushing away in the direction of itself. So those are my two forces. And if I add them like vectors, I'm going to get an F net right there. Okay, so let's just try it with each one of these. Here I have an electron that has a minus charge, so it's going to be pulling towards. Let's make a big exaggerated arrow like this to say pulling towards. And then this is going to be, again, pushing away with a smaller arrow because it's farther away. Now if we add that together, notice that the X components have partially canceled each other out, so this net force is smaller than that one. This arrow is longer because the X component here has partially canceled out the X component there. Okay, now let's try it again. Here's your E. E is going to be pulling on Q, so it's going to be a little arrow in this direction. P is going to be pushing away because those are both positive. This is going to be a big arrow. Okay, so I can do a vector sum there. And then I can do the same thing here. This is pulling towards, so it's going to be big arrow toward because it's closer. And then this one is farther away, but it's also negative, so it's going to be pulling toward. And when we add these up together, the X directions add together. So look, there's our fourth one. Okay, so what I want you to do visually now is to compare these. Notice that because my in my X direction, these are going in the same direction, and in my X direction, these two are going in the same direction. The magnitude of my A is equal to the magnitude of D. On the other hand, over here, not a great drawing, but I hope you can see it, the magnitude of the X direction, or the X component of this summed vector for B and C is going to be smaller. So A and D are bigger than the forces from C and D, which are equal. Okay, so I've also given you an example like that for your homework, which I want you to think your way through. So those are two sort of conceptual level vector sum problems. Now I warn you, this problem is quite a headache. When you actually put in all the numbers and ask for, can you give me the force as a vector, it turns out to be quite a bit of work. So it says, in the figure below, what are the magnitude and direction of the three net electrostatic forces on particle E due to the other three particles? All four particles are fixed in the xy plane, and they have these teeny tiny little charges. Now, remember, E is 1.602 times 10 to the minus 19th. So Q1 effectively is minus 3.2 times 10 to the minus 19th. Oh, that is 2e. So on force on 1, we have a charge of minus 2e. On Q2, we have a charge of 3.2 times 10. Okay, so that's a plus 2e. Remember, that's so it says 2 electrons down. Q3 has a force of this, so that's 4 electron charges, so that's plus 4e. And then finally, your central charge, which is the charge that's going to be, that we want to calculate the force on, is going to have a force of, or a charge of plus 2e itself. Okay, so conceptually you can already see what's going to happen here. This is going to have the biggest force because it's the biggest charge, so it's going to repel. So there's one of your force vectors. On the other hand, these are oppositely charged, so this is going to pull towards it. And these are both positive, and it has a smaller charge, so it's going to be about half of the size. So eventually what we're going to have to do is we're going to have to take this plus this plus this third one, and that's going to give us our F net. Okay, so that's our F net is going to be somewhere over there. Doing this is a real headache though. So I hesitate to put this in the video, but I think it is important to see how we do all of the gory details. So remember, our F is going to be 1 over 4 pi epsilon naught times Q1 times Q2 over R squared. Okay, so what does our force 1 look like? So I'm just reminding ourselves here, this is 2e, this is 4e, this is minus 2e, and this is plus 2e. And they give us distances here as well, which are going to be important. So D1 is 3 centimeters, so let's put that as 0.03 meters. D2 and D3 are going to be 2 centimeters, so that would be 0.02 meters, 0.02 meters. Okay, so our F1 is going to be our hardest, and it's going to go ahead and be in this direction. Okay, so we're going to have to go ahead. It's going to be in a minus x direction, a minus y direction. So it's going to be the amount of force is going to be 1 over 4 pi epsilon naught times, I'm putting that outside, so our two forces, force in the center, force on the side, it's going to be 2e minus 2e over 0.03 squared. And then to get the x component of that, I'm going to have to take it times cosine of 35 degrees. And that's going to be in the minus x direction, so I'm going to put a minus on there. And then for my y direction force, it's going to be minus 2e times, and I'm just going to put the remember there are absolute values on these, and so it's going to be 2e times 2e. The minus here is telling me about the direction of the vector over 0.03 squared. sine of 35 degrees. Okay, so there's your F1. Now, what is the force of F2? F2 is going to be pushing down because these are both positive, so it's going to be pushing in this minus y direction. So again, it's going to be 1 over 4 pi epsilon naught times, in the x direction, the force is 0 because it's not pulling in the x direction, it's just pushing in the y direction. So this is 0, comma, and it's going to be minus, that's giving me the direction, 2e times 2e over, what's the distance? 0.02 meters squared. Okay? And this is all in the y direction, so I don't have to, I'm not going to do my cosine sine stuff. Okay, then my F3 is going to be 1 over 4 pi epsilon naught. All right, and then here I'm going to go ahead and let's see, this is going to be a positive and a positive, so it's pushing towards the minus x direction. So this is going to be minus, that's giving me the direction, 2e times 4e over 0.02 squared. And I'm going to go ahead and now go ahead and this y direction will just be 0. Okay, so how do I go ahead and add these together? Well, I'm going to add this plus this plus this, and that'll give me my F net in the x direction. This plus this plus this will give me my F net in the y direction. Now I'm going to do something a little bit sneaky. I'm going to, each one of these has e times e, e times e, e times e, e times e. So I'm going to take that out. 4 pi epsilon naught. And each one of these has 0.01 squared. So I'm going to take that 1 over 0.01 squared out, and that's just going to leave me with 2 times 2 over 3 squared, so 3 squared is 9, 9 times cosine of 35, and this is going to have 8, so this is going to be minus 8 over, and then 2 times 2 is 4, minus 8 fourths. Okay, and then right here, I took out my 0.01 squared right there, and so I'm going to have 2 times 2, so it's going to be minus 2 times 2 is 4 over, and this is 3 times 3 is 9. And then sine of 35. And then this one was going to be minus 2 times 2 is 4. And then 2 times 2 is 4 again. So that's going to ultimately just turn out to be 1. Okay, so then I have F net equals e squared over 4 pi epsilon naught. This is just 10 to the minus 2 times 10 to the minus 2. So this is going to be 10 to the 4th. And that's in units of meters to the 4th, if you're keeping track of that. And then this is going to give you minus 2.36. And this is going to give you minus 1.25. Okay, now if I want to go ahead and that's effectively my F net, but this is hiding my units in here. Okay, so if I want to find the magnitude of that, the magnitude of my F net is going to be E squared, so that is going to have to be 1.602 times 10 to the minus 19th coulombs. I'm leaving out some units just because I don't have space to write them all. Squared. And then the 1 over 4 pi epsilon naught, that's that K out front, so that's going to give me a 8.99 times 10 to the 9th. Okay. And then I'm going to have to do my Pythagorean theorem because this is my x component, this is my y component, so it's going to be 2.36 squared plus 1.25 squared. Okay, so if I plug all of those numbers in, I'm going to get a very small force. I'm going to get 6.2 times 10 to the, oops, let me try to get the number, 10 to the minus 24 newtons. All right, so I've done that, and now if I want to find the direction, well, I can use that, I can just use this thing for that. If I have a minus 2.36 and a minus 1.25, I can find my angle 1 is going to be tan minus 1, inverse tangent of just this over that, the opposite over the adjacent, so it would be 2.36 over 1.25. That angle 1, it turns out, is 27.9 degrees. And then if I wanted to find out the total angle, if this is my 0 degrees, this is 90 degrees, this is 180 degrees, and add on the 27.9, my total theta would be 180 plus 27.9, which would give me around 207.9, or let's just call it 208 degrees. Okay, so that was a lot of work, and you can see why if I give you a problem like this, usually I'm not going to even put one on an angle because it makes the problem really hard. Not hard in terms of, conceptually difficult, but hard in terms of actually cranking through all the numbers and getting an answer. So I would not expect to have more than one type of question like that on a test, and I would not expect even to put an angle in there if you have to do it on a test. Okay, now it might have occurred to you, this only really accounts for point charges. What happens when I have objects like the rods and things like this in your lab? Does this just mean that Coulomb's law is not really that useful? Well, it turns out that it's a little more useful than that. And the reason is you can have these shell theorems, which essentially, just like we had in our masses, we could say the mass, if it's spread out through the object, acts on the center of mass, and you can have the force of the first object added up, all of these little individual forces add up on some center of mass. In the same way, if you have charge on a conductor, it doesn't spread out uniformly through the conductor. It sits on the surface of the conductor, it turns out, because all of those charges are trying to run away from each other. They're all repelling. So the charges are sitting on the outside. They're spread out as much as they can be spread out. And it turns out you can prove that the total force, if you have like two spheres of charged objects and they're far enough apart, it approximately acts as though it were at the center of the particle. So we don't often talk about center of charge, but it's effectively the same as the center of mass in this case. And another interesting corollary of this sort of thinking is that if I have a particle that has charge on the outside, let's say that you have a hollow metal sphere, for instance, the charge will spread itself over the surface, and if I put, for instance, a minus charge inside, it turns out that for the reasons that we were showing in that earlier conceptual problem, this charge on one side and the charge on the other side are always going to be equally pulling on it. So the overall charges on that little charge on the inside turn out to be 0. So those are kind of interesting little consequences if we take Coulomb's law seriously. Now, the idea of forces adding together to 0 is the idea of equilibrium. And we say that a particle is in equilibrium when the forces on it add up to 0. And so I've given you a homework problem this week which asks about charges summing up to 0. And here we show of 4 situations in which a charged particles are placed on an axis. In which situations will there be a point to the left of the particles? Okay, so over here, where an electron will be in equilibrium. All right, so an electron is a minus charge. So we're thinking about over here, a minus E, minus E, minus E, and minus E. Now, to be in equilibrium, it would mean that one of these charges has to be pulling and the other one has to be pushing. But since one is closer than the other, the one that's closer has to have the same amount of force as the one that's farther away. Let's see. Is that possible? Well, here the thing that's closer has a smaller charge, and it's a minus and a plus charge, so these are going to be attracted. So here's the force from your plus Q. On the other hand, your force from this one, these are both negatively charged. The electron has a negative charge, the minus 3Q has a negative charge, so those are going to repel each other. So those are going to be opposite direction. Now this one has a bigger charge, but it's farther away. So it is possible for those two to be balanced. So this one's yes, this could possibly be in equilibrium. Let's see another example here. Well, these two, the Q and the E, are pushing apart because this is they're oppositely charged. On the other hand, this 3Q and the minus E, so this is the force of the minus Q. These are oppositely charged, the minus E and the plus 3Q, and so they're going to be pulled together. And so in this case, again, they are pulling in opposite directions, and they are the smaller charge is closer and the larger charge is farther away. So again, this also could be in equilibrium. Now, let's look at this other case. Minus E plus 3Q. So this is going to be a bigger force because it's closer now. So there's my force of 3Q. Pulling towards because minus E and plus 3Q are oppositely charged. On the other hand, minus Q is farther away and it's a smaller charge. So that's going to be a smaller force always when I'm over here on the left. So this is a no. That cannot be in equilibrium. These two forces cannot cancel each other out. Same situation here. The minus E and the minus 3Q, big force this way and much smaller force pulling our electron towards the plus Q. And so because this is always going to be smaller than that, this one cannot be in equilibrium. Okay, so I've given you a problem in your homework to think through that idea. Equilibrium means the total force sums up to 0. Okay, so that's hard. Now let's hopefully do an easier part of our lesson. So the idea of electrical current is not too terrible. If a charge is moving around, the amount of charge that passes the surface per unit time is current. Okay, so current is in terms of charge per unit time. Now, since our good units on charge are coulombs and our good unit on times is seconds, our units of current are after this dead scientist ampere, and our units of current are coulombs over seconds. So 1 ampere is 1 coulomb per second. It tells you how much charge is passing by a surface per unit time. Now, there is a hook that is a little bit confusing. And that is that you have to define a direction for your positive direction of current. Now that has always been true because we always had to say, that's my plus x direction. This is my plus y direction. Something like that. But the tricky thing is that you can get a positive current in two different ways. You can get a positive current by having your plus particles go in the direction that I've indicated, or you can have your minus particles going the other way. So a minus in the minus direction gives you a plus. Minus times minus gives you plus. Plus times plus gives you plus. So there are two different ways to get that positive current. One is to have the positive charges moving in the positive direction. The other is to have the negative charges moving in the negative direction. On the other hand, there are also two ways to get a negative current. A negative current is going to either be a plus charge moving in the minus direction, or a negative charge moving in the plus direction. So you don't have any homework problems this week that are going to force you to think about that. Remember, the things that are actually moving in most circuits are going to be electrons. Of course, in semiconductors, well, this is not an of course. In semiconductors, you sometimes can have positive charges. But for our cases where we're thinking about like electrons moving in metals, you're usually going to think about electrons, the negative charge carriers, moving. But it is totally fine for every sort of problem that you're going to do in this course to think about positive charges flowing. It won't hurt you at all. And so just to do a very quick problem in this, it says, what if we think about the return stroke of a typical lightning bolt as a current of 2.5 times 10 to the 4th amps, and it exists for 20 microseconds. How much charge is transferred in this event? Okay, so we have the current I is equal to the change in Q, that's our charge, over the change in time. So what have they given us here? They've given us I, the current, is 2.5 times 10 to the 4th amps. Now this is a lightning bolt, and I want you to be aware that is a very large current. That's much larger than any current we're going to encounter in the lab. We are typically, if you have like a 3 amp current, that is already very big for the lab. So this is an absolutely enormous current. And the time is very small. So 20 microseconds, 1 microsecond is 10 to the minus 6 seconds. So we're talking 20 times 10 to the minus 6 seconds. So that's my amount of time, and so if I want to find how much charge, my delta Q is going to be I times delta T. And so in this case, my delta Q is going to be I, 2.5 times 10 to the 4 amps. Amps is coulombs per second. And then the amount of time that I have is 20 times 10 to the minus 6 seconds. So in that case, the seconds cancel out. I have 2.5 times 20 times 10 to the 4 times 10 to the minus 6. Okay, so 2.5 times 10 is 25 times 2 is 50 times 10 to the 4 times 10 to the minus 6 is 10 to the minus 2. And then this has units of coulombs. So this is coulombs. And this is going to give me 0.50 coulombs. So what this should tell you is that a coulomb is actually a ton of charge. Remember, one electron has about 1.6 times 10 to the minus 19th coulombs. So approximately 10 to the 19th coulombs are in, charges, 10 to the 19 electrons are in 1 coulomb. So a coulomb is kind of a silly unit. More often you're going to think about like microcoulombs or something like that in terms of practical applications. Now, if you're wondering, why is it that lightning is dangerous? It's because your heart is a little electrical pump. And of course, in the early days when they started experimenting with using electrical chairs to kill people, they had some very grisly accidents and would set people on fire rather than stopping their heart. But the usual way for people to die from electrical exposure is because you get shocked and the electricity that flows through your heart, the current that flows through your heart disrupts the current that pumps your heart's natural pacemaker. So I've put a couple links in the PowerPoint if you want to look at that. Here's something about the heart's electrical system. And also an interesting article that I read while I was preparing this was why lightning disproportionately kills the poor. It turns out in our houses, because we have plumbing all over the place, now usually if you're living in a first world country and your house is hit by electricity, that current just goes through the wires into the ground rather than, hitting you. Okay, so next week what we're going to do is we're going to start to combine types of forces. The way that we're going to do this is to establish Coulomb's law by combining gravitational and electrical forces. And this is an interesting problem from your book. I encourage you to try it if you have a few extra minutes. It says, if you have a small angle, and what they mean is if tangent of theta is approximately equal to sine of theta, show that you can make a relationship between x and all that stuff. And I'll show you how to set it up. I think we'll postpone this problem till next time. But what essentially you have to do is you're going to have the gravitational force pull this way. You're going to have the electrical force pull that way. And you're going to have a tension force pull this way. Okay, force of gravity, electrical force, and then the tension force. And so what you need to do in a problem like this is you would split up your x direction forces, which would be your, for this particle, for instance, this would be theta. Your x direction forces would be your electrical force minus, here's your tension force, T, and you're just going to take the x component of that, so it would be T sine theta, and that's equal to 0, because these are two charged balls and they're just hanging out there. And then the y direction, you'd have your T cosine theta minus force of gravity equals 0. And if you put in your electrical forces as 1 over 4 pi epsilon naught Q1 Q2 over r squared, and you put in your force of gravity as mg, you can work it through and get this. So I'll do that in our next video, but not today. So where are we going with this? Well, today we've really hit hard this idea of adding together forces. Where do these forces come from? Well, we want to bundle them together and say, instead of having to think about all of the forces that are acting, let's think about the field. So we did the same thing here where we had a gravitational field that was causing gravitational forces. So on Friday we're going to move forward and try to have an electrical field that causes electrical forces when you put a charge in it. Okay, so this is already long enough. What have we talked about today? If multiple charges surround another charge, the Coulomb's law of forces add as a vector sum. Current is defined through a surface and tells us how much charge passes per unit time. Equilibrium is when you have the sum of all forces acting on an object equaling 0. And next time we're going to talk more about how gravitational and electrical forces, which can both act on a particle as in that example, can also be thought of as consequences of the gravitational and electric fields.